Can you see my slides?
Yes, sir.
But somehow I am not able to see. But you people are able to see my slides?
Yes, sir. Yes, sir. It's visible.
Okay. Because I have also joined from another device, but I can't see this thing. What might be the reason? But because I am unable to see.
Some of participants are saying they are not able to see. Anupam, are you able to see at AICT Academy? It's not.
So the screen is available.
Let me again share. I think even I am unable to see. So
Now visible. Yes. It's visible now, sir. Yes. And chat box. It's visible to me, in fact.
just let me share them. I am sharing the whole screen actually. Uh, uh, I hope that you can see now. Hello.
It's yeah. It's zooming out. Yeah. It's visible, sir.
Okay. Okay. See, before I start my lecture, if you are, of course, I am also trying to monitor whether it is properly visible or not. See, we will have a very brief introduction of sliding mode control, some of the methods by which we can design sliding mode control. We will also see how we can design for power converters. In this lecture, I will, before we go for, say, sliding mode or any robust control, so let me ask you, because I am told to keep this lecture level at very introductory level, and I will try to see that we can actually gain out of these 2 hours of lecture. Okay, can you define what is control? Like when we are saying, but can we define what is control? Can any participant tell me that what you mean by control? I answer that you are allowed to speak. No? Means I mean to you can turn on your microphone and you can speak or not.
I think, sir, we need to unmute the specific person only.
Acha, then I think let's not. Okay. So let me.
They can type in chat box.
If you can type, that is also fine. So okay, I understand that you can't speak unless you are permitted to speak. Before we go for variable structure and sliding mode control, I want to ask you that what do you really mean by control? See, when we say control, so we will also say that how we are actually achieving the certain, for any system, we have a certain objectives to be achieved. If we consider very simple example of any motor control, so your objective may be to achieve a specific speed, fine. So for that, any system will have a certain objectives to be achieved. Sometimes you also want to have that the system operates at a highest efficiency point, so you can have a multiple output from the system, fine. And is the representation of input-output behavior of a system. So it can have a multiple inputs, fine, and multiple outputs. Same way you can, and then system is represented by some way, fine, some set of relationship by which you can express the inputs and outputs and their relationship between them, fine. So what when we say control, what we are trying to say that our ability to keep those outputs or to meet certain objectives. It's not necessary that only output should be set to specific level, but they also can have a certain combinations. Those combinations are also to be set at certain level. But in a very simple terms, we can say that control means to obtain desired output or goals from the system. Fine. So see, this is very broad definition. It means that your desired output or whatever the goals you have for a given system to obtain the desired output goals from the system. So what do you mean by system then? Of course, you can't directly speak, but if you want to say type, anybody can define a system, what you really mean by system. See, we are trying to say that to get the desired output or goals from the system, that is what is the control. Fine. So control enable you to obtain the desired output or desired goals from the system. Fine. Whatever desired goals you have for a given system that you are trying to obtain. But then what you mean by system? When we say system, is there any way for you to define the system? Can anybody type what you mean by system? Okay. See, when we are trying to say the system, it means that you can have two or more than two components interacting to obtain certain desired objectives. So you have a two or more than two components. They are working together in a coordinated way to produce the desired output or to produce the desired outcome. So that is what is the system. So, so system requires at least two or more than two components. Fine, they are coordinating with each other. Then you get the desired outcome. Okay. So what we are trying to say here that we are trying to obtain the desired output goals from the system. So how to achieve this particular part? For that, we design a control system, and yes, some of you might have studied at least introductory course in control system, in which you mostly studied transfer function-based classical control approach, and of course, time domain approach as well as when you are considering the root locus or state space and so on. Fine. Okay. So so now another question which will come here that how to represent the system? Like, see, what are the ways by which we can represent the system? See, representation means how do you express? Because the system is physical, but we want to analyze this system. So there must be some way by which we can represent the system. So when I say the representing the system means I'm trying to ask you that how to model a system. So what are the ways by which you can model? Fine. Model means it's not necessary that we always go for mathematical model. We can also think of a variety of ways by which we can represent the system or we can express the system, fine. So system expression can have a multiple approaches. So one of the approaches what we widely use is the mathematical modeling, fine. We express the system by using differential equations, algebraic equations, algebraic plus differential equations. So this is what normal approach we use, but it is not only limited to that particular approach, the modeling of the system. The modeling can also be done through graphs. The modeling can also be done through multiple other ways. So we need to keep in mind that modeling is not only mathematical modeling, but there are multiple different approaches which we can deploy for representing the system. But mathematical models definitely have certain advantages over other approaches, and that's why we widely use this mathematical modeling, because that allows us or that enables us for analysis of the system under different scenario, which may occur in actual real system, and therefore it becomes much easier for us to analyze that system, fine. So see, we have understood two things, like what is control, what is system, and how to express the system, means how to model the system. There are three important concepts we have discussed. The basic understanding of control. So control ensures that you get the desired result, fine. Uh, so now when we are going for, see, we are discussing a robust control method. So sliding mode is one of the robust control methods. So why do we need robustness? Like the question here is that why I need a robustness in my system? What is the necessity of having this robustness, or why to ensure the robustness in my control? So that question occurs because when we are trying to represent a system, see, whenever any physical system is represented, there will be always certain approximations. Like even if you are trying to consider the very simple system like DC motor, even in DC motor, we when we try to express this DC motor system mathematically, we make lots of assumptions. We assume that there won't be any saturation in poles. Even pole tips will not have any kind of saturation. We will assume that resistance, inductance, and coefficient of friction, all these remain a constant. They will not change with time. But actually these assumptions do not remain valid, and multiple times this in most of the systems, the parameters of the system do not remain always constant. They are subjected to various changes, fine. See, any system, if you want to represent, like if I want to represent any system, what are the ways? Like a system can be considered as a set of associated with the set of variables. So if I say that this set of variable is say x1, x2, up to xn, fine. The other thing is like the set of parameters, right? If I say mu1, mu2, mu m. And of course, there will be mathematical relationship between this x1 to xn and mu1 to mu m. But these are the variables, so definitely these variables bound to vary, fine. And this mu1 to mu1, they are the parameters. So these parameters are normally assumed to be constant. So in case of DC motor, say you may have a second order model, or you can also think a very simplified first order model also if you're considering speed control. But in case of any order you are considering, so this model will have a certain variables. If it is a second order, so then you may have a two variable. If it is first order, you may have only one variable. So variables bound to change with time, that is obvious. But the parameters normally we assume constant, like mu1, mu2, mu m. But these parameters may not remain constant. They may change with respect to time. So in case of DC machine, your parameters may be say mu1 may be armature resistance, Ra, your mu2 maybe friction coefficient, Fr, and so on. Fine. Even mu3 can be your moment of inertia of your rotor and whatever the load you have connected. So many such parameters actually do not remain constant, and they vary with respect to time. So my question was, why do we need the robust control? See, the need of robust control, fine. So today what we are going to discuss, that is one of the robust control technique. So any model is obtained by some approximations and simplifications, fine. The parameters of the system may change, which change the model. So parameter changes, so model will also change. So for some system, we have external disturbances. So if you are putting your vehicle on cruise control, so in that you are going for a certain specific speed, say 70 kilometer per hour, and you have a suddenly opposite wind which is increasing in speed. So what will happen, that these are the external disturbances. Your cruise, now your engine has to produce more power to overcome the resistance which is offered by that opposite wind speed, right? Even in many systems, these external disturbances are very common. Sometimes even sudden change in load can also create disturbance. Like if you have a power converter which is operating at a certain load, suddenly 80 percentage change in load take place. So that will suddenly may drop the voltage. In some of the cases, it can reduce frequency momentarily. So all those, or increase the frequency momentarily. So these are the some external factors which can actually cause disturbances to the system. So see, any model, when you are trying to model, because you can't model everything, you need to only see the essential things which can be modeled, because you also want to keep your model trackable and simple, fine. And when you are trying to do, you always end up with some approximations, some simplifications, so that you can actually have a model trackable, and also you can easily analyze that model. But that will actually add the difference between the actual system behavior and the model what you are trying to produce for the same system. Both may not behave in an identical way. So there will be gap in the actual system and the model what you are using. So then the parameters of the system may change, and which actually changes the model. So model also is not the same what you have used for design of your controller or design of your estimator or whatever you are trying to do with the system. So that model may not remain same. So for some systems, we have external disturbances, right? So there are systems which always subjected to some kind of external disturbances, and you also need to overcome. So because of that, your control has additional task. The control has a task that it can handle the model mismatch. So what are the requirements from the control side? So it should address model mismatch. it should address parameter variations, fine. That also becomes part of change in model, but sometimes parameter variations occur very slowly, and that also can be addressed because it can drift the system performance from the desired ones. So then it should also address external disturbances, fine. Okay, so then this control is not only producing the desired output from the system, or it is achieving the desired goals for the system, but it is also ensuring that in spite of very approximate knowledge of the system, in spite of parameter variations in the system, and in spite of external disturbances, the system output remains the desired one. Fine. So in spite of all the three factors, you still want to have a desired output from the system. So these are the basic requirements for any robust control. So because of that only, several robust control techniques were developed. So sliding mode is one of them that was developed much earlier in erstwhile USSR, and subsequently it actually in late 70s it became actually popular outside Russia, and a lot of people then developed this technique, and now it is one of the matured control technique which can be used for multiple applications. Okay, so let me just give you. See, when we are trying to say system model, you have all studied at least transfer function. That is also one way to represent a class of system. So this class refer to, if you have any question, you can always type, or if you can speak, that is also fine with me, because this is more like a tutorial on the subject. So see, what is the job of control? That ultimately, if you see, as I explained you, that system is expressed by two sets of variables. The one is the state variables like x1, x2, xn. The another is the mu1, mu2, mu3. All are the parameters of the systems. Fine. So even parameters can vary. So what is the job of control? The job of control is to ensure that you achieve your desired goal in spite of variations in your parameter, in spite of variation in your model, and in spite of external disturbances which may be present for some class of systems. Okay, so if you want to see graphically what is the purpose of control, so the system model is in a very generic way we can define like x dot is equal to fx plus gx. This fx need not to be a linear function, it can be a non-linear function, fx plus gx into u of t. So u of t is the control variable, fine. This is in our hand. So I can modify u of t the way I wish it to be, and then I can achieve my desired objective. You can say that uh, your objective means at any time I may be somewhere here, fine. So suppose this is my initial conditions, that is where I am present, and my objective is to bring this is the state space. I hope that some of you may have ideas. So state space means what? We are representing our variables x1, x2, x3 up to xn as various axes of the n-dimensional space, and our entire trajectory will evolve as a various subcomponent of this axis, which is x1, x2, x3, because if I have my state here, then the projection on x-axis will give me the variable x1, projection on x2 axis will give me the variable x2, and so on. Fine. So if I have a n-dimensional space, or say two-dimensional space, so in that way, in two-dimensional space, I will have a x1 and x2 as variable that can be represented as a plane. So I can represent it as a x1 and x2. If it is a three-dimensional, I need to use x1, x2, and x3. But in general, we say n-dimensional state space in which I can evolve the trajectory from any initial point to the desired point. So I am initially, so whatever my initial point, the from that point I can have a projection on x1, x2, x3 up to xn axis, and that will give me the respective component on those axes. Fine. So what we are trying to say, that what is the control problem? The control problem is that you design u of t such that you steer that any initial value, like initially you may not be at 0, but you want to go from any initial non-zero initial condition to 0. Fine, here you want to reach. So there can be multiple approaches. It's not only one approach by which you can, because there are so many paths. Fine, somebody can reach here also in this way also. Fine, this origin. So somebody can think of reaching here also this. So there are multiple paths, and there are different uh, approaches through which you can actually reach to origin. So the control problem is that you are at any non, this you can consider x as the error. Fine, x you can consider as the error between the actual value where you want to reach and the actual state where it is right now. So ultimately your intention is to uh, derive this or force this error to 0. Fine, so you want to reach to origin in your state space. That is what is your control problem. So this problem is also called the regulation problem, because you want to regulate your state variable at certain point. Fine. So like your speed you want to regulate at 2000 rpm in case of DC motor. In case of power converter, DC to DC converter, output voltage you want to keep at say 75 or 100 watt or 120, but that value is fixed. So that's why we call these kind of control problems as the regulation problem. Fine. In some of the cases when the missile tracks the target at that time, surface to air missile, so the target is continuously moving, so that's why the missile also needs to continuously change its position, and it has to track the target. So these kind of problems actually come in tracking problem, in which your final goal itself is continuously time varying. Right? The point where you are trying to reach is not a stationary, but that is continuously varying with respect to time. So you have a tracking problem. So the control, so we will initially focus only on the regulation problems. So where you are trying to regulate some variables at a certain desired level. Fine, but those desired levels are fixed, and that's why it is considered as a regulation problems. Okay, so your control problem again, if we can discuss, then you have to design u of t such that xt reaches the closer to origin or reaches to origin. Fine, your objective is to reach to the origin, but many times if you are reaching sufficiently close to origin, that is also adequate. Fine, many control problems don't require that you reach to, say, you want that x should reach to xd, so your x minus xd should go to 0. But if you are saying that, okay, your x minus xd is smaller than some very small number epsilon, that is all right. It means that you are in a neighborhood of origin, but not at the origin. But reaching to the neighborhood of origin is also fine. Okay, so this is what is the system model, and I hope that most of you know that so robust control we have already discussed. See, many times there are two applications of robust control. See, once there was very extensive wind damage, and in the second case there was a this was a extensive wind damage in one application in aircraft. This is in aerospace, we have to use the control because all the applications are open loop unstable. So without control it is impossible to actually fly this aeroplanes. Fine, passenger or any military aeroplane, it's not possible to fly without you have a closed loop control. So very extensive. So the model entirely changed when you have a severe wind damage. The second case, even one engine was failed. So when there is a complete engine is failed, but there was another, of course, you have a two engines. So second engine actually used to land the aircraft safely. So in both the cases, because of this robust control technique, the aircraft was landed safely in both the cases. Fine. With severe wind damage, see, loss of engine is much more severe problem compared to the wind damage, but still it was possible to uh, control the aircraft in a safe way and also to land safely. Fine. Okay. So there are lots of applications in which you can actually use this robust control. So let me now start very basic introductory discussion on robust control. There are also lots of other applications like microgrid and where you can use the sliding mode control power converter. There are multiple such kind of applications where we can use it. Okay, let me now start. See, well, let's consider the LTI system. See, you know that linear time invariant system, if it is, we will also focus initially on scalar system. It means that your U belongs to R. Means in general for multiple input system, you can also have a U belongs to R M, where you have a M inputs. Fine. But just for keeping the discussion simple initially, we will consider that U belongs to R. Fine. Okay. So uh, what is our objective? So let me start with that. In general, we can express our system like x dot is equal to ax plus bu. Fine. So, so what we are trying to say here, your x will belongs to Rn because it's an n-dimensional space. Uh, because we are considering n-dimensional system. If you have a DC motor, it can be first order or second order depending on how you model. So your many power converters will become second order system like boost converter, buck converter. They normally modeled as a second order system. Fine. You also know that why we say some system as second order, some systems as first order. Fine. I hope that you all are clear with that. Okay. So your A belongs, it's a matrix that is n cross n matrix. B belongs to R m cross n matrix. But sorry, this is n cross m matrix. But most of the times, right now we are taking m to be 1. So B belongs to R n cross 1. Fine. So and X of course belongs to Rn. So this is the system which represents some physical system. Fine, this represents physical system. So A captures what? The matrix A and B captures the parameters of the system. See, when we say LTI system, linear time invariant, so when we are saying linear time invariant, it means also that my A and B matrices are the constant matrices, fine? These are the constant. But I can also have a situation in which the system is linear, but time varying, in which my A and B matrices will not be constant. They will also vary with respect to time. Fine. So that kind of system can also be there, but our focus will be, say, a linear time invariant system. So let me start with one first order example, like what is control we are trying to achieve here. Okay, suppose my system, the first order system. The first order system, which I am considering, say, x dot. This is the first, only one state it has, which is x only. That is ax plus bu plus rho x t. Okay, here x belongs to R. So on the scalar, A also belongs to R, B belongs to R, and rho xt also belongs to R cross R plus, but just consider this is a scalar only, fine. So because it has a two parameters, that's why we are modeling in this particular way, but it's a scalar. And what we are trying to say that rho xt is also uncertainty, is unknown function. We do not know the value of this rho xt, right? What we know is only upper bound. What we know about this function is only that rho xt is smaller than or maybe equal to rho m. This is a rho m is a rho m belongs to R plus. Fine, it's a positive number. Okay. So what I don't know the exact value of rho xt. What is a is a constant, u is input, fine. So u belongs to R, and this is the input. Okay, so what we are trying to say here, see this also, there are multiple systems which can be modeled as a first order system, fine. So even HVAC, the room temperature control can also become first order system. Even DC motor control also becomes first order system. So there are many practical systems which can be modeled as a first order system. Many valves actually behave as a first order system. So first order system does not imply that it lacks the application. So there are lots of systems can be modeled as a first order system. Now the problem with the what we want, like see what I want, that this x should go to 0 as t goes to infinity. Fine, x will go to 0. So as t goes to infinity. So I need to design some u of t. Right? I need to design some u of t uh, such that this happens. Fine, x should go to 0 as t goes to infinity, asymptotic stability. Fine. So how to achieve that? That this xt is not available for me. Doing that thing is very straightforward. Fine. So suppose rho xt is not available. So I have a x dot is equal to ax plus bu. So what I can say? I can say that u is equal to say minus b inverse and say beta x. Fine, I can do this way. So beta is some positive number which I need to find out at what should be the value for the stability. So if I say that if rho is not present, then how can I ensure these things? So you can see that to ensure that part, if I substitute this, this is an open loop system, fine. If I substitute this control in a closed loop to make the system closed loop, then what happens? X dot is equal to ax plus b, and for u I am putting minus b inverse some beta into x. So then x dot is equal to ax minus beta x. So I will have a minus beta into x. Fine. So a minus beta into x. So what can I do for the stability? My requirement. So a minus beta should be less than 0. Fine. It means that beta should be greater than a. If that is suppose a is equal to 2, so I can choose beta to be say 3. So in that case, my this thing will be x dot is equal to minus x, and you can easily see that this will actually lead to stability. Right? e raised to minus t into x 0. This is the solution of this differential equation. So this will ensure that x will go to 0 as t goes to infinity. If I choose, because for stability, I need to ensure that this remains negative. A minus beta should be less than 0. A is already known to me. Only beta is the one because this is the control we have chosen. Fine. So this control we have chosen. So obviously all the parameters are in our hand. This beta is the only parameter we introduce through the control, and we can say that we can actually stabilize this plant by appropriate choice of beta. I can choose the beta so that a minus beta. See, also remember that our we are providing the feedback, fine. So x is the state variable, and our u is also using that x, fine. So it is minus beta minus b inverse into beta into x. So it is a feedback which we are providing in the system. So ultimately, that is why we are seeing that our system stabilizes. So this appears to be simple, and we can easily handle this kind of system with state feedback. Fine, state feedback because our U is using the state, and you are feeding back that input in the system. That's why we call it as a state feedback. Uh, okay, but see what will be the problem if this A is a parameter which is not always known to us. If it is not a constant, suppose it is varying, we are saying A is equal to 2, but it can have certain variation around that, some delta plus or minus. So in that case, what can happen? Still, I can ensure that system remains stable by choosing very large value of beta, but the problem here is that you may not get the similar kind of performance. Fine, but you can also have some external disturbances. Like what disturbances we have considered here? If you see the original system, it does not have only deterministic part, but it does have a non-deterministic part. What is that non-deterministic part? That is rho xt. So that non-deterministic part is also available here. So this non-deterministic part we have to address somehow. Fine. Uh, okay, I hope that all of you got the idea. For the first order system, we consider the system with uncertainty, and after that we design very simple controller. If there is no uncertainty in the system, designing the controller for deterministic system is very straightforward, but it is not as straightforward as the system with uncertainty. Fine. When you have a system with uncertainty. So how to address that particular part? Let's discuss that particular thing. Fine. So how to handle that part? For that, we need to change our controller. Now, if I consider the original system, like x dot is equal to ax plus bu plus your rho xt, where only I know about the rho xt is only that I know it's a bound. Fine, rho m. I know that I know only rho m about this uncertainty, but see what happens here that but rho xt, if I say that this is my rho m positive and this is my rho m negative. See, this is plus rho m, this is minus rho m, but rho xt can be anything. Means suppose in between if I put the 0, so suppose somewhere here I am putting 0, so this is the 0. So it can be anything. Means uncertainty can be like anything. Fine. So it can lie. So it's not that it is always rho, but it can be anything between plus rho m and minus rho m. Fine. So all the time, this uncertainty can be of this order. Fine. So so what to do in this kind of situation, like when you have a such kind of uncertainty? So we can see before even introducing the sliding mode, we can see that we can address this issue. Means in fact, we can ensure that x will go to 0 as t goes to ts. Means we can have a finite time stability for this system, not always. because it is first order system. That's a finite time stability is possible here. But of course finite time stability is not a problem. But suppose if I go for a state feedback, then if there is exogenous disturbance, then there is no way for me to ensure this particular requirement, that x will go to 0 even if t goes to infinity. In spite of stretching t till infinity, it may not be possible for me to design a controller which ensures this requirement to be met. Fine. So, so let's consider for the system the following following control law. So, u of t is equal to say minus how it has come. We will discuss subsequently. So, control design is very straightforward in sliding mode. Only the other part, the surface design, requires a lot of careful attention. Okay, so I will say that this is say B inverse. Why B inverse? Because B is already multiplied here. So just to remove that B, we are writing B inverse. Then I am saying some Q. Q is a positive number, and as signum. So or I can write the complete sine of x. Right? Only sine of x we are taking. Right. So if x is greater than 0, then sine of x will be like plus 1. If x is less than 0, then sine of x will give you minus 1. Fine. And if x is equal to 0, sine of x is not defined there. Okay. So so this is a signum function, the sine function or signum function. We normally call it as a signum function. So signum function is utilized here. This is even without knowing the sliding mode, you can understand what we are doing. So let's substitute this particular equation here. So see q, you will be choosing such that q will be always greater than rho m. Fine, that is what we will ensure. This is how, because we know the rho m about the uncertainty. We know only one thing, the upper bound of that. So if I now analyze the closed loop system, so the closed loop system will be what? The closed loop system will be ax plus b, then substitute this b inverse q as gn of x plus rho xt. So then you will have here AX. This will be minus. Okay, I will also add one more thing just to simplify. This also without that we can do, but I'm trying to just simplify, and I will add one more input here, that is AX. AX just to cancel this AX. Even without that we can do, but I'm just trying to keep it a bit simpler so that it remains. So what is my control? The control is B inverse, then Q SGN of X plus AX. Fine. So I just substitute here again, rewrite minus B inverse Q SGN of X, and then again minus B inverse AX plus rho xt. Then I will have a ax minus here I will have a q SGN of x. Then this should be plus, sorry, this is plus already. Okay, so this then it will be minus ax plus rho xt. So this AX will get cancelled, and I will be left with only two terms, minus Q SGN of X plus rho XT. Okay, just only see that my control law I have given like this, minus B inverse, then Q SGN of X plus AX, fine. B inverse just to because I have a u multiplied with b, so b inverse into b will become unity, and this ax also, in my closed loop there is a ax, so I do not want this ax, and I want to cancel that ax, so that is the another thing. Okay. So what I want to do here, that okay. So your closed loop system, if you look at minus q SGN of x plus rho xt. Now, the closed loop system we need to analyze properly, fine? Because because in you have a signum function. So signum function means there is a two possibility, fine? So x can be, say, x greater than 0. In that case, my x dot is equal to minus q plus rho xt, fine? If and if x less than 0, then x dot will be uh, plus q plus rho xt. So this is a closed loop, fine. So we need to see that whether this is a stable or not. How to ensure? We only have taken that q is greater than rho max, fine. In both the cases, that is the scenario. So now x is greater than 0 means what? I can check that what is happening when x is greater than 0. So let's see that this is uh, horizontal axis is the time, the vertical axis is for x of t. Here the time t is equal to 0. So what are the value you have initially? That is, say, x of 0, fine. This is a positive value and this is a negative value for x of t, fine. This is x of t, but after 0 you will have a negative value, and if x of initially at t is equal to 0, if x is greater than 0, then x0 will be falling here, fine, in the positive part. So for the positive part, say equation 1 is applicable. For negative value of x, equation 2 is applicable, fine. So now see that x dot is equal to minus q and plus rho xt. So now q is chosen, which is always greater than rho m, fine. Suppose it is possible that rho can be plus rho m, because this rho xt, if you see, we have already seen that it can be plus rho m maximum value, the minimum value is minus rho m, fine. So both the possibilities exist for rho m. So if we can consider worse, because see, what is my aim? I am at here and I want to reach the origin. X, this is the line t is equal to 0. There is also the line for x is equal to 0, fine. This line is also for x is equal to 0. So I am here and my interest is to reach to x is equal to 0, fine. So how to reach x is equal to 0? So if you want to reach to x is equal to 0, it means what? If you look at this first equation, if your x0 is greater than 0, which we are considering as one case, if x0 is greater than 0, it means that your x dot should be less than 0, fine. X0 is greater than 0, it implies that x dot means your rate should be negative, then only you can go from that positive value to 0. Means if x0 is, say, 10 here, fine. Suppose if it is a 10, so your x dot should be negative, so that it will reduce from 10, it will become 9, 8, 7, 6, 5, 4, and it will reach to 0, fine. That is what you want to do. So look at this equation, whether your x dot is negative here, because rho is not known exactly. So we can consider the worst case scenario, that rho is equal to rho m, find maximum positive value. But in that case, what will happen if I see this equation, if the equation 1, if I consider that the uncertainty takes the maximum value, so I will have a x dot, which is minus q plus rho m, fine. This is a positive value. So, but you know that q is always greater than rho m, because q is chosen because it's a design parameter, and we have chosen always greater than rho m. It means that this x dot is less than 0, because you have a larger negative portion than the positive portion in the equation in the right hand side, fine. So you will have a x dot which is less than 0, fine. It means that if you're starting from here, and see, rho is continuously changing, so the what is the rate, the negative rate may not be constant, it will continuously vary. Sometimes if rho m is very low, then maybe rate is higher. If rho m is even negative, then rate is even further higher, fine. So it will continuously change, and it will remain always negative. Fine. The only question which we can answer is that it will reach to 0 because it is always continuously decreasing. The way it decreases, it also depends on rho xt. Fine, it's not a constant rate. It cannot be a straight line. Fine, but only thing which we can ensure in no case that rate will increase, but it will continuously decrease. Fine. So this actually graph does not represent because some of the places like here it is increasing, but it is not the case. It has to always decrease. Fine, decrease, and so only we have to draw in such a way so that it always decreasing. Fine. So uh, so it will always decrease. Fine. So the rate of decrease also doesn't remain constant. But now when it reaches 0, fine. So it will again may cross this line also. Fine. It may again cross this line also. But now let's see the situation when x is negative. When the x is negative, the second equation is applicable, the equation number 2. When x is negative, we know that this equation is applicable. See, when x of, say, even initially you can have a starting time also x can be negative. Fine. So when x0 is less than 0, and you want to reach to this x is equal to 0 line, then what should happen? Then the derivative of x of t should be greater than 0. Then only you can reach. Fine. If it is a negative, then it should increase with respect to time, and then only it can reach to 0. Fine. So let's consider that second equation first, and then after we will see that what happens when it reaches the 0. Fine. That behavior we will analyze after some time. Okay, so what we have proved that if x0 is less than 0, if initial condition is, because there are two possibilities, initial condition can be positive or it can be negative, because only two possibilities exist as we have a first order system. So if x0 is less than 0, then also what will happen that because we have proved that x dot will be greater than 0, because this equation q is positive, rho xt is can be positive or negative. Even if it is negative, because q is always greater than rho xt, so q minus rho m will be again positive number. Fine. So x dot will be again positive. Fine. X dot will not be a negative, even though rho xt is negative, the maximum negative value. So q is chosen is greater than the maximum negative value of rho. So therefore it will be always positive. So I can again start in a similar way. So I can start and I can, this can reach here. Fine. See, now the moment it reaches to the, say, from negative to positive or positive to negative, so either equation 1 or equation 2 will be applicable. So again, you know that the moment it becomes negative, so x becomes negative, the rate becomes positive. And whenever x becomes positive, the rate becomes negative. So again, it is the moment it crosses here at this point, so it has x has become negative, but the rate will become, the second equation will be applicable, and rate is again positive. So again, it will be forced back. So it will continuously slide on this particular line. The same thing will also happen here. Fine. So whatever the initial condition it start, it may chatter here because the practical implementation will have a sampling effect, because we will be sampling the state and then taking the control. So all these things are not instantaneous, and therefore you can see the line will be chattering, but it will remain in the close proximity. In an ideal sense, if you have an infinite switching, because this switching will take place at x is equal to 0 line. Fine. Because you see the original your equation, so this signum function, when x is equal to positive, it will become +1. For x is x less than 0, it will become -1. So your x dot will be minus q plus rho xt closed loop, or plus q plus rho xt. So this switching will continuously take place. If there is a possibility of infinite switching, then you can see only the solid line here. So the trajectory will start from any non-zero initial condition and keep sliding on this, and it will always remain on that. So remember that your system does have unknown function, that rho xt. In spite of that, it is possible for us to ensure the stability of the system, means x goes to 0, X goes to 0 means X is the error. That error will go to 0. So your X actual state will go to the desired state, right? So this is possible just because your this is possible just because you have a this nonlinear function, that is a signum function, which is introduced in the control. Fine. So this control ensures that your desired goal of reaching to x is equal to 0 is met in spite of disturbances. Fine. So desired objective for the system was to keep this thing 0, and it is keeping that thing 0 all the time. If you have an infinite switching capability, then it will always remain at this particular juncture. So see this motion which is occurring because of switching function or the nonlinear control what we have introduced. So this is the trajectory. The trajectory here has only one element, that is x, and that is confined to this particular x is equal to 0 line by external control. So that behavior is called the sliding mode behavior. Fine. This is a first order system, so that's why it is slightly easy for us to understand how this is happening. So there is a control effort which is always pushing that it remains on this required line. Fine. It does not allow, because there is a force here. Here you can see that here it's a minus q and here you have plus q. So this both the control forces are ensuring that you always remain on that. Fine. If it tries to deviate from here, there is a force which will force the trajectory to remain on this line, and if it deviates from the other side, then there is another force plus q that will ensure that it will remain on that particular line. So in spite of system uncertainties, in spite of external disturbances, system will always remain x is equal to 0 line, right? So this kind of motion is actually called sliding mode or sliding motion. Or you can also see that your control structure is not constant depending on the value of state. See, what is your control? So you are saying the signum of x. So depending on the your control state variable, so you are changing the structure of control. Fine. So in variable structure, that was the initial concept through which the sliding mode is one of the uh, subdomain of variable structure. Variable structure is used for a very broad methodologies, set of methodologies in which you are deliberately changing the structure, and sliding mode is one of them. Right. So here you can see that your structure is changing. So your closed loop has minus q or plus q depending on the value of x. Right. So that's why you also call this class of control techniques as variable structure control, in which the control structure is dependent on the values of state. Right. Okay. So this is the first order system. So what about the second order system, third order system, or general nth order system? How to define the sliding mode control for general nth order system? That also we will briefly see, and how to design this sliding mode controller for that. Here we have directly taken our controller as, say, B inverse into Q as Gn of S minus AX, just to overall simplify the closed loop, but we have a systematic procedure through which we can always select the control. Fine. You need not to worry about designing the controller much. The main challenge will be in the design of switching function. Okay, so let me now see what happens for the second order system. So what that in case of second order system, I will have a x1, x2, fine, two state variables will be there. So the sliding mode control actually is an indirect control. So what we normally do, this I'm just explaining for the second order system. Uh, we design some desired function, and we will try to vanish that desired function in finite time. Okay, What I mean by this, like suppose if I draw a line here, it's not necessary that for second order I should have only line. I can also have a plane, fine. But now let's keep the discussion simple initially. I am just confining myself to a line for a second order system, right? So to express this line, I need only one variable because it is passing through the origin. And my the same way, like I am somewhere here initially, fine. This is my initial condition. It can be here also. It can be anywhere. Fine. Initial condition. What is my objective? My objective is always to reach origin. Fine. I want to reach origin here. Fine. This is where I want to reach. This is my objective wherever I am. It means that my error is non-zero and I want to force that error to zero and always remain at zero. So what we can do, that this is the line we have to choose, fine. This is the chosen line, chosen. We will also call as a switching function or sliding surface, fine. So we will actually choose this thing particular. So this line we will choose, and what we will try to do that we will enforce our trajectory. It can be anywhere, because see, if you use any control law, then it can actually evolve in a certain way, fine, and it get perturbed because of various disturbances, and it can reach here, fine, by any control law. But instead of doing that, what we will do in sliding mode, how to design this line, we will discuss, fine. So that just trying to explain you in a conceptual way what exactly we do for a second order system. Then after we can extend the similar thing for the third order, fourth order, or general nth order system. So what we will do that we will bring the trajectory and from anywhere to surface. Fine. If I am here, I will try to bring the trajectory from anywhere to surface wherever I am here. Fine. These are all possibilities that I can be available at these different places, because all the possibilities I can be here also. So I will try to bring the trajectory on the line. After that, what we will do, this is always possible, means this line is attractive. It means that trajectory from anywhere, if I design the control appropriately, so this line is attractive, or you can say that sliding surface is attractive, and so trajectory will always attracted towards the line, and making that line attractive is not difficult task. It's the straightforward task which we will discuss subsequently. So once you reach on line, what will happen, that you will ensure that this trajectory always remain on line, fine. Always it will remain online, and eventually, because this switching function is stability is guaranteed. So once you are online, so you will always reach to origin because of the stability which is ensured, fine. So from wherever you come, even if you are coming from here, it will remain on this line, and it will actually ensure that the stability of the uh, surface, fine. Because of the stability of the surface, you will reach the origin destination, which is your uh, uh, goal also, fine. This is your destination. So this destination you will reach, and this destination you will reach in a way which will not be affected by any kind of disturbance. See, if disturbance try to perturb the trajectory, but your control will always ensure that it remains on the surface and it will not allow it to deviate, fine. So this is for the second order system. So what also happens here, that when you are confined this trajectory on line, so the second order system behaves like a first order system, because for line you require only the line which is passing through the origin requires only one variable to express it, fine. So you require only one variable, and the other variable is dependent on that. So your system behaves like a first order system. So your model is also reduced by one, fine. Your input is one, the system is of second order, and the system order is also reduced by one. Okay, but uh, what about the third order system? So third order system, what will happen that in that case, you will have a plane. Okay, so what you will try to do that sometimes it's difficult to visualize, but you can say that you will define a plane which is passing through the origin, and you will force the trajectory any point, because this again this entire plane what you are designing, the surface, or you can say in general hyperplane, fine, because it becomes line in case of second order system. If you go with the traditional approach in which you are trying to reduce the model also, so, so line becomes for the second order system. For second order, it becomes line. For third order, it becomes plane. Not necessary. It can also be a plane for a second order system, and it can be hyperplane for third order system also, fine, and plane for third order system. And as you go, then we will use the general that hyperplane. Fine, for fourth order, fifth order, and all those things are difficult to. So there will be hyperplane in which if you are, then it will actually remain always on that plane and reach to origin. From wherever you are actually forcing the trajectory on that, it will reach to origin. Fine. So when it remains confined to certain hyperplane, what we define. So line is also hyperplane in a broader context. So when you are confining your trajectory to remain on hyperplane, what you are ensuring? You are ensuring that your system will be robust. It will not deviate because of the disturbances, and it will actually reach to the origin, your destination, and it will remain there in spite of disturbances and all external variables. Just like what we saw the first order system, same thing we can also see for the second order system, third. See, beyond third order, even for the third order system, it's not very easy to visualize all these things. So we will only rely on the mathematical abstraction when we are going for, say, third order, fourth order, or beyond that system order. We can't actually visualize. When it becomes very difficult to visualize any hyperplane because the equation will have a several state variables, and it's not easy for us to visualize. But of course, that is also not required. We can actually very strong abstract concept can be utilized to prove all the attractiveness of the hyperplane and existence of sliding mode and other aspects. Fine. So they need to be attractive. Okay. So let me now go for the nth order system so that we can actually discuss that how to achieve this particular part. Fine. Uh, any question at this stage, Manmohan, or anybody who is handling this? If there is any stage, any question at this stage, I can answer, and then we can go to the for general nth order system. Anybody has any question? You can raise your hand, and then you can be given access to microphone and can speak. Does anyone have question? Okay, I think there is some question. Let me read this. What if the chosen line is, how can I get this? Just I'm trying to get access to these comments. Can anybody help me how to get? Saw that somebody has written the question, but I'm not getting access to these uh, questions. Are they available? Just a second. Okay, I think one question I could read. Other question I just saw on Flash. Somebody saying that okay, this is very interesting question. That someone is saying that what if this line is time varying? Yeah, it's very interesting question. That see, this line need not to be stationary. The question is, sorry, this is just assume that this line can also vary. There are lots of research in which to improve the performance, this line is varied. So this line can be completely non-linear, time varying, not necessary that it should be a linear line. I mean to say expressed by linear function. It can be non-linear also, and also it can be time varying. So you can see lots of results in which to improve the performance, this line slope is continuously change. Fine. So this line can be time varying. That is completely all right. But see, only because it's a control, so you need to ensure the stability. Fine. To stability cannot be left without explicit proof. So you have to ensure the stability explicitly when you are going for non-linear sliding surfaces or time varying sliding surfaces, linear but time varying. So time varying sliding surfaces are possible, and these are widely explored in the literature. Fine. So you will get lots of paper in which time varying sliding surfaces are used. Other question, because this I could read on Flash. Can someone help me with how to get these comments? Because it came like a flash and then disappeared. So I'm very familiar with this system, but today I'm not able to get. Let me see if I can get from here these comments. Chat. Okay, there are some questions. Okay, some people have also written. Okay, how x0 x is equal to ensure that error is zero. See, your x itself is error. I said you that you can write your equations in error coordinates. So assume that x itself is your error. I could have written the other symbol like e. So rather than using e symbol, because this is very common practice in control literature to use x itself as error in case of regulation problems. Fine. So x itself you can treat as a error, and then x is equal to 0, the error is also 0, because otherwise you don't want any system that everything goes to 0. It has no meaning. Fine. So when I say x1, x2, x3, they actually represent the error in x1, error means error in say they represent actually e1, e2, e3, e4 like that. If you are more comfortable with that kind of notation, but in control literature we normally use x1, x2, x3 just to represent the error in those coordinates. Fine. So consider in that sense. So what if the chosen line is second order system is varying? That I have already answered. That is very much possible. How x and error is 0? That again I have already answered. That consider x is your e variable, error variable, and because it's only matter of nomenclature, and if x goes to 0, your error goes to 0. So rather than considering x as a state variable, you can consider x is the error in the state variable. Fine. If it is x1, then it is actually the error in your first state variable. So that is how you should consider. Okay, I think I do not have a more question, it seems. So we can actually now again go back to design of sliding mode controller for nth order system. Okay, so let's consider that your system. So see, for any system, what happens here, like, let me first try. I am considering deterministic systems, fine. And let me just consider that B rho xt. So it is a uncertain system. Rho xt is uncertainty, fine. So there is uncertainty in the system, and this rho xt is nothing but the uncertainty. So
What do you mean by,
uh,
sir? What do you mean by uncertainty, sir?
uncertainty means it can be variations in parameters, like A matrix contains variations, all the parameters, and the uncertainty can also come because of the external disturbances. Say the external disturbances coming off, as I gave you the example, even in say wind farm, the wind speed suddenly increases beyond a certain level or the direction changes, so that can be considered as external disturbances. When your vehicle is working in a cruise control mode, suddenly the wind, opposite wind increases its speed, so that can be treated as external disturbances. But within the system you have a lot of unmodeled dynamics. Actual system has certain unmodeled dynamics which you have not considered in your model, so all these things can be clubbed into one single term, and that can be written as rho xt. So it is also
Uh,
multi yeah.
like what I'm comparing it with the state space model. By state space modeling, we get this x dot ax plus but, and this
Hmm.
is the new term which I'm seeing.
Hmm.
This is called as uncertainty. So
Hmm.
I need to know how you are modeling the uncertainty. Like you are representing it with the row x comma t.
Okay,
How
okay.
do you model it?
Yeah, I understood. Let me just suppose I have a deterministic system like this. So what happens if one possibility that A contains all the parameter, B also contains all the parameters. So what I can say that A is actually behaving this way: A plus delta A into X. Then this is B plus the delta B into U of t, because B is never constant. A is also not constant, but it has some variations of delta A, and here you have variations of delta B. So what you will do, that you will say that this is A x dot is equal to AX plus BU plus delta AX plus delta BU. Fine. So now you have an uncertainty part which is coming because you don't know what is delta A. That delta A keeps on changing. Delta B also keeps on changing. So what you will do, that you will club all this uncertainty and represent it as what I have done here, that B rho xt. So B rho xt is nothing but this particular part which is coming because of variations in parameter. The parametric variations are captured in matrix A, and the actuator related parameters are captured in matrix B. But if you, because ultimately actuator is also part of system, so ultimately they are part of system parameter, and variations in them, you can say that it is B rho xt.
Okay, so what I can understand that in state space, like all the parameters we took, it's constant and it's a constant matrix because we inject some disturbance and we bifurcate the disturbance and the DC value, and the DC value is kept as constant. So the value of A and B are constant, but here the parameters are varying.
Yeah,
Uh,
actually,
uh,
most of the
so
system this happens, but for ease of modeling, like otherwise handling this delta AX term and delta B UT terms are slightly more intricate, and to avoid that complexity in analysis, we don't consider. But parameters do not remain constant. We say, of course, A matrix and B matrix, both matrices remain constant. However, that is not the case when you are actually considering the real scenario. These parameters, even your inductance will saturate at certain current, and that saturation is also non-linear. So inductance value will not remain same at a lower value of current, and when it is almost like fully loaded converter. So inductance values will differ there. So even capacitor will be subjected to aging effect and other things. So all these things are what we are considering as constant may not remain constant in many applications depending on where you are operating. So that's why disturbances and load disturbances also occur, because suddenly you see that frequent changes in load. So but load disturbances are inevitable in any system. It cannot be considered as constant in any system. But otherwise also you have a situations in which you also subjected to some external disturbances. Parametric disturbances are the internal disturbances which are occurring because of the system physics, right? System behavior, systems physics, that yeah, creates that internal disturbances. But you can also have some external disturbances. So to abstract all these disturbances in a single term, so one way is that we can represent it as a B rho xt. Why it is multiplied with B? Because we are considering it as a match perturbations. I will come later, but right now assume that this is nothing but the perturbations, fine. But it is actually multiplied with B, so it is also called the match perturbation. Okay, did I answer your question?
Yeah, I understood. So we are just heading towards more perfect modeling. That's it. That's it. That's what we are doing now.
Yeah, so we are taking into account all these variations. So overall, our performance remain better, and also our the stability and other things are proved considering all these disturbances. Fine, we are not neglecting which are actually present in the system. That's what is the main purpose. Okay, so my purpose is to explain you how to design sliding mode controller for general nth order system. So here we are not saying it's a first order system. It is I explained to Rn. Only I am saying that this is right now I will consider U belongs to R. So scalar system, single input system, but this can be easily same way extended for multiple input system. Fine. Okay. So let me now go for this. So the only assumption we are putting is that rank of P is equal to M. In our case, M is equal to 1 for a single input system. Fine. So B is a full rank matrix. If there is a deficiency in the, these are very few systems. Some mechanical system only can have a situation where the matrix B may not have full rank, because these systems are under actuated system. That happens because of some robotics applications, and some mechanical systems exhibit that kind of behavior. But for most of the power converters and other systems, electrical systems, ensuring the rank of matrix B is equal to M is almost straightforward. Fine. This always observed in most of the electrical system. So this is not a strong assumption that matrix B is of full rank. So that is not a that does not create any problem in terms of limiting the application. That's what I want to say. Fine. So only that assumption is required. So see what we can do now. We do the coordinate transformation. So what I will do, I am already in X coordinate. I will go to X coordinate to Z coordinate. Why I am doing this? I am doing because so that we can easily design the sliding surface. See, there are two things which we can again focus here. In any sliding mode controller design, you have a two steps. Sorry, you have a two steps. The first step is design of surface. This line what we are designing, or hyperplane we are designing. So, or you can say design of hyperplane. And the design of controller. You can also say this as surface design. Design of switching function. So there are multiple names we can use, either hyperplane design or surface design or switching function design, because this is a function which decides the switching. So design of hyperplane, surface, switching function, all these things come under this particular category. So first thing is the design of stable hyperplane. Fine. So design of controller is almost like can be put in autopilot mode. If you have a stable surface, you can always come with this design of controller for most of the systems. Right? It's not difficult. So step 2 is much simpler, straightforward, design of controller. Only step 1 requires a lot of creativity, and all your requirement, your all objectives and goals for the system is to be incorporated in step 1. Once you are done with step 1, step 2 is straightforward. Fine. For most of the system, step 2 does not require much creativity. Of course, certain applications where you want to reduce the chattering, some creativity can be used in step 2. However, step 1 requires all the design goals to be incorporated, and properly stability is also to be ensured. Fine, then only you can go for step 2. So this two-step design is there. So what we are doing now, we are on step 1. So to design the surface now, it's a hyperplane, it's an nth order system. So if you have a m is equal to 1, then your hyperplane order will be n minus 1. So it's not possible for us to visualize what we can do for the second order system. So that kind of visualization is impossible here. So what we need to do, that we need to actually you rely on mathematical abstraction, so that we can actually prove the stability and other things. Okay. So we will see to do the transformation. So I will define coordinate transformation as coordinate z is equal to tr into x. The TR can be orthogonal matrix. So even if you are not aware about, but just consider that transformation matrix. So you go from one coordinate to another. It's a linear transformation. Fine. If it is orthogonal, then inverse of TR is nothing but the transpose of TR. That's what you can use. It's a real matrix, and so we will use this. So what is the advantage of this? So TR is chosen in such a way so that when it operates on B matrix, then it partition the B matrix in this particular way. It will have all the zeros and B2. So here you have a n minus m rows, and here you have a m row. In our case, if m is equal to 1, so you will have n minus 1 rows, which are all 0, and the last row which will have a one non-zero element, which is B2. So here B2 in general matrix belongs to m cross m, and that is the invertible matrix, because what we have assumed that matrix B is a full rank matrix. Fine. If it is a full rank matrix, then it has to be invertible. If m is equal to 1, then it's just scalar element. So that scalar, any non-zero scalar element, it is always invertible. Fine. So in our case, B2 can be R only. So it will be just some number. Fine. So that is always invertible. So you can always find the inverse of that in case of scalar system. Okay, so what does this system do? Now let's see that original system is x2 is equal to ax plus bu plus b rho xt. So if I multiply this entire system with tr, so I will have a tr into x dot, tr ax, tr bu plus TRB rho xt. So what we will do now, I will actually see TR into x dot. You can easily see that this is nothing but the z dot. So here we have defined this way. So z dot is nothing but TR into x dot. So I can directly write here z dot. Then I can write here TR A X, I can write as TR inverse into Z. Then TRB, we already know that it is available. So I will define this TR into B as equal to BR. So I will call this as a BR matrix, which is nothing but the having the n minus m rows which are 0 and the last m rows which are non-zero, fine, with the matrix B2, or in our case it's a scalar, so just last row which has a non-zero element. So I will call it as a BR into U of t. Same thing, TR into B will become BR into rho xt. Fine. So so now this matrix like TRA, TR inverse, I will call this matrix as AR. So I will have C dot is equal to AR into Z plus then I will have a BR U of t plus BR rho xt. See, now what we'll do that we will partition this entire system into two subsystems, right? So entire subsystem, because you know that BR matrix is of this form 0, B2, and AR system also I will partition, because you know that here I have a n minus m rows and this is m rows which are non-zero. So similarly, I will also partition this AR matrix. What I will do, so I will put my partition in a very similar way. So partition will be n minus m rows, and then I will have a m rows here, fine. And so I will have here A11, A12, A21, A22, right? Here also you will have n minus m and m. So partition. In our case, it is m is equal to 1. So here it becomes only last row, and here it becomes only last column of ER. Fine. But we are doing in that way. Okay, so Z also, what I will do that Z also I will say partition into two component, Z1 bar and Z2 bar. Fine. So what is Z1? Z1 bar belongs to R n minus m, and Z2 bar belongs to R m. Fine. And if you want to properly define, so you can say that Z1 bar is nothing but Z1, Z2 up to Z n minus m, and Z2 is nothing but Cn minus m plus 1 to C n. Fine. In our case, see, what will become that Z2 will become just 1, that is a Zn, because in our case m is equal to 1. But I am just giving you the general formulation also for m input system. We can also use the similar formulation, fine. But you can easily understand that when m is equal to 1, your Z2 will become just Zn, and this will become n minus 1, fine. Your G2 bar, sorry, this is Z2 bar is nothing but this, right? So Z2 bar is just Zn in case of first, in case of m is equal to 1. So what we have done, like, see, it's very simple why we have done here. The only thing is like I want to partition the B matrix as 0, B2, fine. So that's why if we are partitioning B matrix, then corresponding partition to be done for the A matrix also. So the A matrix also we have partition in this way. So finally, if you see what am I going to get, I will get the following. I will get the Z1 bar is equal to A11 Z1 bar, A12 Z2 bar, then Z1 bar dot, fine. Z2 bar dot is equal to A21 Z1 bar plus A22 Z2 bar plus B2 U of t plus B2 rho xt. Fine. This is what is my original system, which is transformed into x coordinate to z coordinate. Fine. Z1 is equal to, because this is what? This is n minus 1 dimensional system. And this is m dimensional systems, right? For m is equal to 1, the second equation will become the scalar because m is equal to 1 there, and the first subsystem will become n minus 1 dimensional system, fine, when m is equal to 1. So you can see that now the input is only in the second equation, fine. Input is only in second equation, and the first equation does not have that input. So what we will do now is the following. So now we will define the switching hyperplane. Fine. See, we don't know how to design so far, but we can always first define that this is how the hyperplane can be defined. So we have a see, Z1 and Z2 both are vectors, right? It's not a one single state variable. Z1 bar and Z2 bar both are actually vectors, right? State vectors, but in a Z coordinate. So that is what you need to keep in mind. So what I will do now, that I will say that switching function sigma, that is sigma t, that is defined as, we also use sometimes like s of t. Both the notations are fine. So I will say that it is, say, C1 Z1 bar plus C2 Z2 bar, right? C1 and C2 both are matrices of appropriate dimension. See, for m, suppose now let's consider that m is equal to 1. So sigma t or st, this belongs to R. Right? So this will be a scalar function, right? If it is m is equal to m, in that case, this sigma t will belong to Rm. Okay. So what will happen, that you will have a multiple surfaces, and intersection of those surfaces will be your destination point. That will include the origin where you want to reach. But let's not right now worry about that part. Let's take the case in which you have a single input system. So this sigma 2. So this is what is your hyperplane, because this is defined in nth order system. So this C1, ultimately you can see C1 and C2 both are matrices. So this is, you know that Z1 is nothing but Z1, Z2 up to Zn minus m, and Z2 bar is nothing but Zn minus m plus 1 to Zn, right? So this is the function which is defined in n-dimensional plane, and your objective is what, how to design C1 and C2. That is the main question. Fine, we have to ensure that stability is always guaranteed for whatever the values of C1 and C2 you use. So ultimately, for any linear uncertain system, your main goal is to design C1 and C2. If you design C1 and C2, and then you are done, because the control design is almost straightforward, which we can always design. Fine. So what we can do to design this C1 and C2. So assume there exists u of t such that sigma t becomes 0 in finite time. See, this is always possible. As I said, that design of u of t is very straightforward. So therefore, we will right now assume that there exists ut which can vanish the sigma t in finite time. This finite time is very important. Fine. So sigma t becomes 0. See, if sigma t becomes 0, this implies what? This implies that the C1 bar plus C2 bar also becomes 0. So dimension of C2 is m cross m. If you see that appropriate dimension, what line I have written, so the dimension of this C2 is always m cross m. It's a square matrix, and we are choosing, so it has to be chosen so that it remains invertible. Fine. So I can write here it C2 bar is equal to minus C1 bar. So Z2 bar I can write as minus C2 inverse C1 bar. See, we can also see one thing, that when I am defining this surface, I really do not initially deliberately I have taken C1 and C2, but if you see very carefully, then you realize that there is no need of C1 and C2 both. I can choose C2 to be, say, identity matrix, and still I can have a complete control on the behavior and the design of switching function. Fine. So many times we do choose C2 to be identity. That's also one possibility because it doesn't add any value in terms of design. Fine. So this is universal. Fine. It's not only we are choosing here, but it can be chosen for any kind of system because it doesn't add any value in terms of, or doesn't give you any extra flexibility in design, because I need only one constant. So let me take C2 to be identity. So I m cross m, and in that case, my Z2 bar will be minus C1 Z1 bar. See, this is when the sigma t is equal to 0. Remember that these Z2 and Z1 both are the state variables. So state variables are linearly related. It means what? I can say that now when the sliding mode is achieved, means sigma t becomes 0, means I am achieving the sliding mode. When the sliding mode achieves, at that time, the Z2 variable depends linearly on Z1 variables. Fine. So when these state variables are linearly dependent on each other, so you should not treat them as state variables. Fine. Because you should, because the first condition is that there should not be any linear dependency on the state variable. If they are linearly dependent on each other, then they should not be considered as a state variable. Fine. So what happens that during sliding mode, if Z2 variables are linearly dependent on Z1 variable, it means that you are getting the reduced order model. So system in sliding mode behaves like a reduced order model, just like we saw for the second order system. When you confine your trajectory on line, at that time it was behaving like a first order system. Fine. So same thing here happens, like your system behaves like when m is equal to 1, then system order is reduced by 1. Say m is equal to 4, then system order is reduced by 4. In general, the system order is reduced by as many inputs you have. Fine. If you go in that way, because there are other ways also of designing the sliding surface. In those cases, even model is not reduced. But in this case, if you follow this approach, then your model will be reduced. Now you see that now we converted the actual system into two subsystems. Fine. Actual dynamical system into two subsystems. You can say system A here and system B here. Now Z2 depends on linearly on Z1, so I need not to consider the B subsystem here at all, because my system is completely dictated by Z1. If the Z1 is stable, see, ultimately what I want, that Z2 should go to 0, Z1 should also go to 0. See, if they are linearly related, if Z1 goes to 0, then Z2 will automatically go to 0. Fine, I need not to worry about the stability of Z2. So I need to only ensure that Z1 should be stable. It means that I have to consider only first subsystem here. That is Z1 bar dot is equal to A11 Z1 bar plus A12 Z2 bar. So if I rewrite that first subsystem here again, so that will give me that Z1 bar dot is equal to A11 Z1 bar plus A12 Z2 bar. Fine. So if I substitute the value from this equation, A12, so here I have a minus C1 Z1 bar. So essentially I can write A11 minus A11 bar, A11 Z1 bar, then A12 to C1 and Z1 bar. Fine. So you can see here, this is very famous equation, famous in the sense very familiar equation. Some of you will find that if I want to say C1 is the design parameter, and it's a design function or design variable. So here we need to design C1. Design C1 so that Z1 bar remains stable. Fine. So for m is equal to 1, A11 is nothing but n minus 1 cross n1. Fine. And A12 works like an input matrix. Like in such kind of system, you might have studied that how to design C1. That's what I'm asking you. Suppose if I have x dot is equal to AX plus BU, then you say that U is equal to minus KX. So your closed loop becomes A minus BK X. So you choose K by using pole placement, by using any optimal technique. So same way, if you compare this with this, then A12 is nothing but your input matrix here. So C1 can also be designed by using pole placement, by using LQR, by using any control technique by which you can lead to stable behavior of this subsystem. Fine. So if I call this subsystem as subsystem C, closed loop subsystem C, so this will actually lead to multiple ways by which you can design the switch, because your switching function has only one parameter, that is the C1. Fine. C1 is a matrix, so that has to be designed. So we can easily design by using the pole placement, by using even Ackermann formula. If it is a first order system for multiple input system, you can't design using the Ackermann formula, but you can use the pole placement technique, robust eigenstructure assignment technique, LQR technique. So all these techniques can be utilized. Even simple pole placement technique, the way you are designing the K here for this linear time invariant system, same thing will be utilized here. So here your input matrix is what? A11. Your system matrix is A11, which is say for m is equal to 1 is n minus 1 cross n minus 1, and your input matrix is A12, and your the gain matrix is C1, which is to be obtained. Fine. So in MATLAB also you use this command using place command and put eigenvalues for by providing A and B matrices. So similar thing can also be done for the sliding mode. So C1 you can design in this particular way by supplying A11 and A12, and then C1 you can design. For obtaining the TR matrix, there are already standard algorithms exist by which you can obtain the TR matrix, which is orthogonal. So inverse is much simpler. Because to reach to this z coordinate from x coordinate, you require TR matrix, right? So that TR matrix can be, or again we can transfer everything to the original coordinate. That is also one possibility. But you can directly, because design is much simpler in this z coordinate, and that is the reason we went from x coordinate to z coordinate, did the complete design, and then after we can actually again go back to original coordinates. Fine, that is always possible. So once you design the C by using either pole placement, which is the simplest technique, or Ackermann formula for first order for one single input system, or by using LQR or using any other technique which allows you to put the poles at a desired location, which are to be stable. So if Z1 is stable, which is guaranteed here, then automatically you can see that Z2 bar will be stable. Fine. So Z1 bar is stable going to 0 asymptotically. So Z2 bar will also go to 0 asymptotically. Both will be stable. Fine. So what I want to summarize that switching, this is only one of the techniques, right? It's not necessary that even this C1 need to be linear, or it can be obtained in this way. You can design in multiple ways. It can be non-linear function, or it can be combination of linear, non-linear function. There are lots of ways by which you can design this sliding function or switching function. And but ultimately all these things will actually incorporate your requirement, like what you want from the system. That is what you have to incorporate here. Fine. When you are trying to design for most of the power converter, the order is not very high, say third order or fourth order, or many converters are just second order. So design is not that complex because of the order is relatively low in power converter applications. Okay, so again, so this is how we will design the C1 matrix. So once you know the C1 matrix, then your function sigma is already known. So you will call it as a C1 bar plus C2 bar, because C2 we are considering as identity matrix, fine. So if you are considering C2 to be identity matrix, so in that case you need not to consider that part, fine. So that Even if you add C2, it doesn't add much because ultimately it will come as a C2 inverse C1. So it's the same constant we have to call. We will call this as another constant C2 inverse C1 as equal to K, and then design the K. But it doesn't give us any extra flexibility. Therefore, we just consider C2 to be identity, and we take only C1, which is to be designed. So once you design the C1, then we are left with only design of controller. Fine. Uh, so anybody is there? Manmohan, you want me to continue, or in the next lecture when whatever you suggest I can do? Dr. Manmohan or anybody is there online? Am I audible? Anybody is there from?
Yes, yes, sir, you are audible, sir.
Yeah. So because I was given 10 to 12. Okay, so let me complete the control part also. See what we want that the sigma t should become 0 in finite time. It actually it must go to 0. So remember that originally in the first order system, we ensured that when x was greater than 0, we say that x dot should be less than 0. And when x was less than 0, we said that x dot should be greater than 0. So essentially what we wanted that this x into x dot should be always less than 0. Fine, both if you are combining. So something like that we wanted that always should happen, so that we ensure that it remains attractive. Fine. So here also very similar kind of condition, like sigma into sigma dot. Sigma is a scalar here. Fine. So consider m is equal to 1. Otherwise, you will write sigma transpose into sigma uh, dot. Fine. So this will become scalar. So, but let's focus right now on this. This should be actually less than 0. But what will happen with this, that this condition will not ensure that sigma will go to 0 in finite time. So what we can do here, that we need to modify this condition. So we will say that sigma into sigma dot should be less than or equal to minus eta mod s, mod sigma. Sorry. Sometimes in place of sigma, we can also use s. Fine. So these are very common nomenclature. So this is called the eta reachability condition, where eta is positive. Fine. For some eta, this condition should satisfy eta reachability. So if you satisfy this condition, so it is always possible that you reach this sigma is equal to 0 in finite time. And that is what is the intention. Okay, so for that there is one approach which is called the uh, in which we try to impose certain dynamics, which is called the reaching low approach. So I will just very briefly discuss and derive the controller for that. So reaching low, what we say here, that in reaching low approach, see, I say that I'm considering single input case. So sigma dot should be like, it should behave like QSGN of sigma. So if this is there, then only this kind of condition is guaranteed. Fine. So to ensure that this condition is met, I will say that this is what should happen. So for that, what we will do, that we know that sigma is what? Sigma is known to us. Sigma, we know that this is C1 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 dot, sigma is equal to C1 Z1 bar plus Z2 bar. Fine. So sigma dot is equal to what? Sigma dot is equal to C1 Z1 bar dot and Z2 dot. Fine. So I will write C1, then Z1 is equal to A11 Z1 bar plus A12 Z2 bar plus A21 C1 bar A22 Z2 bar plus B2 UT. Okay, I will take the system without uncertainty when I'm deriving the control. I will explain how this works. So I have taken only B2 UT but not B2 rho XT. Fine. So entire system I have taken. So I already know that this should be equal to minus Q SGN of sigma. Fine. So from this, because I know that left hand side everything is known, I can always derive the control law. So what should be the control law here? If I derive from here, because B2 is invertible, so I can derive the control law as because all these things will go toward that side, so they will become minus B2 inverse, and then I will have a C1 A11 Z1 bar plus C1 A12 Z2 bar, then plus A21 Z1 bar plus A22 Z2 bar minus QSGN of sigma. This will come within this bracket, sorry. This is plus 5 because this minus is already taken out. So this will be your control law. In fact, we can slightly further simplify because these are nothing but the component of. So if I want to, if you want to further simplify, then you can easily see that this can be written as B2 inverse. Then if this matrix, if we give another name, the matrix in which I have a say C1 and identity IM cross M. If this matrix, if I define as C transpose, then we can easily write this as C transpose AR. AR is nothing but that A11, A12, and then I will have a Z, Z, which is made of these two component minus plus Q SGN of sigma. So I will have something which is of this sort, which can be utilized. Right? So if you substitute here, then you will get this kind of control. See, control law, as I said, that is not difficult to obtain. So control law is kind of a straightforward way by which you know that this G we have already defined as component of Z1 bar and Z2 bar, fine. So this is how, and AR, you know that AR is equal to A11, A12, A21, A22. So means after combining everything, I'm trying to write this, fine. So, so this will have a two parts. One is the linear part, and the another is the this non-linear part, which contains the signum function. So this control will always ensure that your sigma is attractive, and so speaking, the trajectory will reach to sigma, and it will always remain on sigma is equal to 0. So these existence conditions can be always guaranteed if you are choosing in this particular way. There are other approaches also, or we can directly ensure that this condition is satisfied. Ultimately, you have to satisfy this particular condition, fine, eta reachability condition, because it has to go to zero in finite time. If it doesn't go to zero in finite time, then you don't get any benefit in terms of your sliding mode and other thing. Because if sliding mode does not exist or it takes forever, like it takes infinite time, then it has no meaning in terms of providing any robustness. It cannot provide any robustness unless it reaches to the sliding mode. Fine. So I think I stop here, and if there are questions, I can take questions. We will have, I think, one more lecture in which we will see some applications of sliding mode.
Yes.
Are there any questions?
So it's a request from my side. Like if we take an converter next time, sir, when we are having
That is what I was.
We'll
Yes,
take
yes.
fourth order converter, any converter, then we can implement this what you have taught theoretically. Exactly, that will be good, sir. It will be a good understanding then.
Yes, because that is what is the plan. Because unless you understand the basics of sliding mode, you can't directly go for that. Otherwise, it will remain completely superficial and meaningless. So this was the thought we had while I discussed with Professor Manmohan, that this is how I will cover some portion of initial introductory sliding mode control, and then we will go for some power converter design, so that sliding mode for power converter design, so that it becomes easy for all of you to understand. So yeah, next lecture we will have some applications. So any other question or any other input?
Sir, one question in chat box.
Okay, and then chat box I need to see from
Can I
here.
implement this for three-phase inverters?
You can implement for any system. See, the sliding mode is widely applied to various power converters. So sliding mode has like huge applications, right? So even higher order sliding mode is there. So I don't see that there will be any problem for three-phase converter. Even we have applied to various three-phase converters in other places. So you can definitely apply to any dynamic system. I don't see, even for sliding mode is used for estimation as well as identification also. So it's a technique, fine, so that you can always use for different requirements for making the observer robust. You can use this thing. Even for parameter estimation, you can use this technique.
Sir, few more questions. Maybe you have answered. Maybe how x equal to
That I
x
think I answered
zero
that.
ensure
That I think answered those questions. I in the middle I asked, and then I think those questions.
okay.
Is there any parameter to compare chattering effect in sliding mode control? See, whatever the switching function gain is there, that much chattering can occur, because switching function gain is also selected based on the value of maximum uncertainty. So that I think slightly we will see in more detail that particular part, because right now I have only gone to control design but not chattering analysis and other things. So I can discuss that part. And so of course chattering will be there, but there are solutions for chattering, like you can go for higher order sliding mode in which chattering will be significantly less. It will be there, but significantly less. Okay, any other question? I think I answered most of the questions, earlier questions also. So
I think, sir, no more questions. So thank you very much, sir, for delivering a nice talk on the fundamentals of the sliding mode control, which is very much necessary actually before applying it to any application. If fundamentals are clear, then we can have some innovation in that. So thank you so much. Now we will have one more talk by you in the schedule. So where like how to use the sliding mode control on power converters, that we can learn from you. Thank you so much, sir.
yes, sure. Thank you.
Okay. Okay, so well, participants, now we have another lecture at 2 o'clock. So we'll meet at 2 o'clock. Thank you.